9.5 parametric equations. Okay, so a quick note, and maybe this will make you a little more excited. Unlike last week's 9.4 notes, 9.5 notes, we only have 2 pages today, and they're not near as complicated. So hopefully that's a bright note, and you'll keep following me here on this one. So 9.5 parametric equations. So what we have is we're going to take these plane curves, parametric equations, and we're kind of breaking down these problems and adding a new, what we call a new parameter, okay? So it says, suppose that t is a number in the interval I, and a plane curve is a set of the ordered pairs, all x's and y's, that fit my 2 parametric equations, x equals f of t, y equals g of t, for t in the interval I. So t is the parameter, okay? And to maybe make this make a little more sense, t, and the reason we often use it is, let's say, stands for time. So basically what this is saying is, in a moment of time, where on a curve am I at? Okay, so we can have all kinds of curves. We've obviously done plenty this chapter. We know we could have a parabolic, we could have an elliptical, we could have a hyperbolic, we could have a circle. We can have all kinds of curves. And it's saying, in a moment of time, what would the ordered pair be that fits this particular curve? And so what we end up, though, to start with here, what we're going to have are these parametric equations. So we're going to have more than one equation, which breaks apart the x in that moment of time and the y in that moment of time. So we're going to select some values of t on the given interval. We're going to find each value of t using the parametric equations to confine an x and a y that go with that time. And then we're going to plot them and connect them with a smooth curve. So that's our steps, and that's what we're going to try to do on this first example. Okay. So don't be overwhelmed in what is this going. Just kind of follow me here and maybe it'll make more sense. Okay, I'm going to make, I don't even know what I'd call it, not a t-chart because I'm going to have more values. Okay, I'm going to have my time. Okay, and by the way, they give me this interval of between -2 and 2. So I'm going to have a -2, -1, 0, 1, and 2. Don't forget, that's not everything because I could do decimals, but really I don't want to. Okay. I have these values. My x has a parameter equation or a parametric equation of t minus 1. My y has a parametric equation of t squared. And once I find that, it's going to make for me some ordered pairs, x and y. Okay, so here we go for x, the first one. I plug in -2 for t, I subtract 1, I get -3. For y, when I plug in this time of -2, if that's even such a thing, -2 squared is 4. So I end up with this ordered pair of -3, 4. And that's at that moment of time of -2. Okay, second one. We're going for -1. So x equals -1 minus 1, which equals -2. Y is going to equal my -1 squared, which will be -1 squared is +1. So I end up with an ordered pair of -2, 1. Plugging in 0. X equals 0 minus 1, which is -1. Y equals 0 squared. 0 squared is still 0. So I get -1, 0. At t equals 1, I'm going to get x equals 1 minus 1, which is 0. I'm going to plug it in for y. I have 1 squared, which is 1. And I get an ordered pair of 0, 1. And my last one, 2. I plug in 2 minus 1, which equals 1. I plug in 2, which 2 squared is 4, and I end up with the ordered pair 2, 4. Okay, so I took my parametric equations, I plugged in my parameter, which was t, and I end up with these ordered pairs. Okay, so let's come over and sketch what we have here. Okay, remember, this is still an xy plane. This is not a t. There's no t in here. But the t helped me find these ordered pairs, so I'm still graphing them on an xy plane. Okay, so I go to -3, 4. Okay, I'm up here. -2, 1. -1, 0. 0, 1. And 2, 4. Okay? So it says to me, graph them, connect them in a smooth curve. So I started here, and I'm going to connect them, because remember, if we would have plugged in those those decimals, we would have found those. Okay, I start here. That's a definite start point. I am also going to include arrows on my graph to tell them over that given period of time which direction this curve went. And it definitely ends here because I have these parameters of between -2 and 2, and it's equal to those. That's my curve. That's what I'm going to draw. It shows what happened over that parameter from -2 to 2. Okay? Let's move on and let's try another kind, because of course that one seemed a little bit easy, so let's see if we can make this a little tougher, right? And right away you can look at the equation and say, well, these parametric equations look a little more complicated. Okay, so once again we're going to make this kind of this chart, not a t-chart, but a similar chart. And it's important to notice this time that my time is between 0, or my t is between 0 and 2 pi. Okay, so I'm thinking unit circle. If I'm going to go from 0 to 2 pi, I'm going to start at 0. I don't really need a lot of points, to be honest. Let's just go to pi over 2. It's like my 90 degrees, right? Then pi, like my 180. 3 pi over 2, that would get me like my 270. And 2 pi. Okay. And just a quick note, notice it's not equal to 2 pi, so we're going to go up to that point, and maybe they'll join, maybe they won't. We'll have to see what happens. Okay. X is negative sine of t. Cosine, y is negative cosine t. And then, of course, we still get our ordered pair of x, y. Okay, that's still going to be what we're looking for here. But, of course, it plugs in a little different. Okay, hoping you have your gold unit circle handy. You thought that would go away, and it just never seems to disappear, does it? All right, negative sine of 0. Well, the sine of 0 is 0. It's negative. It's still going to stay 0. Y equals negative cosine of 0. Well, the cosine of 0 is 1, but that negative will make it negative 1. So I end up with my first order pair of 0, negative 1. All right, going to pi over 2. Negative sine of pi over 2. That's like 90 degrees up at the top of my unit circle. The sine of pi over 2 is 1. I have that negative out front, so it makes it negative 1. When I do negative cosine of pi over 2, well, the cosine of pi over 2 is 0. The negative's really not going to affect it. That stays 0. And I end up with the order pair of negative 1, 0. Go into pi. Negative sine of pi. Well, the sine of pi is 0, so the negative once again doesn't matter, and I still get 0. I get negative cosine of pi. Cosine of pi is negative 1. Negative 1 times that negative makes positive 1, and I end up with the ordered pair 0, 1. Negative sine of 3 pi over 2. Well, the sine of 3 pi over 2 is 1, and it's negative 1, and the negative of it will make it positive 1. Y equals negative cosine of 3 pi over 2. Cosine of 3 pi over 2 is 0, so the negative. And finally, for 2 pi, I start out with negative sine of 2 pi. That should look similar to my 0 up there. It has a sine of 0, so the negative doesn't matter. And the negative cosine of 2 pi. Cosine of 2 pi is 1. That negative out front will make it negative 1, and I end up again with 0, negative 1. Okay, so once again, remember I'm graphing this on an XY plane. Okay, and I'm going to be honest. It looks like I could make this 1. I could make this negative 1. I could make this 1. I could make this negative 1. My first order pair starts at 0, negative 1. So 0, negative 1 down here on the bottom. Then I go to negative 1, 0. So just to note, I'm kind of keeping track where we're heading here, negative 1, 0. Then I go to 0, 1, which is on top, 1, 0 on the right, and finally end up back at 0, negative 1. Because the first value and the last value actually share that, even though it wasn't equal to, it's going to be continuous. So my continuous curve is going to go like here. Remember, if we had plugged in those 45 degrees and all that, we would still get those curves in the beginning. So don't forget we started here, which means my arrows need to go around so they show that I'm actually going clockwise around this curve. Okay, so make sure you put the arrows there to show exactly which way we went from the beginning. And again, when somebody just peeks at this, they're not going to know where we started. They would actually have to find the values to figure out where we started. Okay, moving on to page 2. So of course we're going to change up what we're doing here a little bit. This time we're going to eliminate the parameter. So they give us the two parametric equations. We're going to graph this in a different manner by eliminating the parameter. Okay, one thing we do need to be careful with, and I'll show you as we do these examples, is we may need to change the domain of our rectangular equation once we get it so it's consistent with what happened for the domain for the parametric equation. So remember, anytime you start switching these around to a different form, sometimes you have to be careful of that domain, okay? Kind of like when we did inverses, if you remember those. So what we're doing here is we're going to eliminate the parameter t. To do that, we're going to get basically both of our parametric equations equal to t. So we're going to get t by itself is what we're going to do. Then we can kind of do a system where we can substitute in, and we will turn then that into a rectangular equation. Okay? So on my first equation, you'll notice I have x equals square root of t. Well, if I want t by itself and just t, I need to maybe square those equations. So I'm going to get x squared equals t. Okay, quick reminder here, because this is going to become important and go back to this rule about changing the domain. Before I change this to get t by itself, it said x equals the square root of t. Well, no matter what t or time or whatever I plug in there, if I'm getting the square root of it, I'm always going to get that, because if I want it to be a function especially, I'm going to get a positive value, okay? So just keep in mind that x is always positive here, okay? And that's going to affect us as we do our go to graph later. So just keep that in mind. Okay, my second equation, I have y equals t minus 1. I want t by itself, so I'm going to add that 1 to the other side, and I get t equals y plus 1. Now that I have t by itself in each one, I can just do a substitute. I'm going to substitute this in for t. I get x squared equals y plus 1. Okay. If I want to make this look like a function, I can see kind of that it's looking like a parabola. I'm going to actually subtract my 1. I'm going to get y equals x squared minus 1. I prefer that. I'm going to be honest for a function. And I'm going to be honest again, I'm not thinking about this parabola like the lattice rectum, anything like that. I'm thinking of what we did way back in Algebra 1 when we graphed parabolas. Okay, so I'm going to go ahead and graph this, okay? Notice this is a rectangular equation. It's a parabola, okay? We think of when we graph these, they make our U shape. The one thing I need to be careful with, though, is that from earlier, and I stated this earlier, my x needs to always be positive, because from my parametric equations, that domain was set earlier, so I need to keep it as well in that same thing. So I'm not going to plug any negative x values in. So if you think about it, if I plug in 0 for x squared, 0 x squared is 0 minus 1 starts me at negative 1. I plug in 1, 1 squared is 1, minus 1 is 0. I plug in 2, 2 squared is 4, minus 1 is 3, and I could keep going. But you can see what's happening is my curve is going like this. I'm going to end it with an arrow because I could go on and on and on with my positive x's. But remember, I had to start on the positive here, and I'm going to join my arrows on this curve to remind me that I could go on forever, and I'm moving up to the right at all times. Okay, so that's kind of that example of watching that domain. If you had to do some math to change to get your t by itself, that's where you have to stop and say, was there a limit or was there a restriction on my domain that I need to follow on my new rectangular equation? All right, moving on to number 4, because once again, we can't go through it without using some unit circle stuff, right? We got to keep these pretty. All right, so let's talk about what's happening here on number 4. I have x equals 2 cosine t, y equals 3 sine t, and I would like to get t by itself. Now, I'm going to tell you right now, we're not going to be able to get it all the way by itself, but I can get it at least with that trig function as by itself as possible. So let's just divide by 2 on the left one, so I'm going to put x over 2 equals cosine t. I'm going to do the same thing on the right. This one is going to be y over 3 equals sine of t. Okay, please, please, please do not try to take the inverse cosine or the inverse sine, because that's not going to make a pretty rectangular equation later. Nothing that we graph has the inverses in there, so please don't try to do that. So we're going to leave it right now in this trig function. And this is one of those that, believe me, you basically just have to kind of get used to things you can do here. So I'm going to try to do a system of equations, but right now I simply don't like cosine t and sine t in an equation. However, I do like cosine squared t and sine squared t. So I'm going to take this liberty of squaring both equations. Okay, so over here, when I square, everything gets squared, right? Everything there. So I'm going to get x squared over 4 equals cosine squared t. Okay, and remember, cosine t is one identity, so it's not like cosine squared t squared. That's just one thing that got squared, so I put the square on the cosine. Okay, so on my second one, I'm going to get y squared over 9 equals sine squared t. Okay, I like working with sine squared and cosine squared a lot better than just sine and cosine. But once again, I really haven't gotten rid of that t. All right, let's think of systems of equations. I can substitute like I did in the last one. I can eliminate, right? Or add my equations together. So let's add my equations together. So I have x squared over 4 equals cosine squared t. And let's add it to y squared over 9 equals sine squared t. Okay. And the reason I like that is think about this on the right. Cosine squared t plus sine squared t. I like that identity. Just a heads up, if you're dealing with secant squared and tangent squared, you might not want them added. Perhaps you want them subtracted. So just room for thought if you run into that on your examples. Okay, on my left side, I'm left with x squared over 4 plus y squared over 9. And now I want to simplify one more time. Obviously, I'm trying to get these t's out of my equation. Well, I happen to know I just set up a beautiful identity, so I end up with this equation, x squared over 4 plus y squared over 9 equals 1. And I no longer have t in my equation. I'm down to a rectangular equation, and it looks exactly like a nice, beautiful ellipse from earlier in this chapter. Okay, so let's get a graph kind of going here. I know I'm going to not have a lot of space, but all right. Thankfully for us, it does give us some pretty numbers here. Let me change colors. Maybe. Ellipse. Quick reminder on ellipse. A squared is the larger number on an ellipse. And so it looks like my a squared here is 9. That means my a is 3. And because it's underneath my y, that means that's going to be my major axis. So I'm going up 3 and down 3 from my center of 0, 0. Thankfully for us, there was no center there. And that means my b squared is 4, which my b is 2. So I'm going to go left and right 2. Remember, those aren't technically vertices, but they do help us graph. And we're going to get this ellipse that goes like this. Okay, we're almost done, but we're not quite done. We need to think about which direction is this ellipse moving, because we need to add those arrows on. Are we moving clockwise or are we moving counterclockwise? Okay, so to figure out this order, I am going to go back to my parametric equations. I'm going to go look at these two right here. Okay, so let's just say I'm going to start with t equals 0. Okay, well, if t equals 0, I plug in cosine of 0. Well, the cosine of 0 is 1 times 2 is 2, so that's going to give me a 2 for my x. For my y, the sine of 0 is 0 times 3 is 0. So my first value, let's go to 2, 0. So I go to 2, 0. I'm right here on the right. Okay. So let's just give one more time here. 0. The next one, let's go pi over 2. That's probably the easiest to go to. At pi over 2. So the cosine of pi over 2 is 0 times 2 is 0. The sine, I'm on my y, the sine of pi over 2 is 1 times 3 is 3. So I go next to 0, 3, which is up top here. So it looks like I'm going counterclockwise around my ellipse. So I'll go ahead and add my arrows in those directions. Okay, so this is turning my two parametric equations into rectangular by getting rid of the t. Earlier, we just did a plug and chug to graph similar figures, okay? So there's two methods to basically get you the same type of graph. Always include your arrows to show which direction the graph is actually moving in over those time periods, okay? That's what we're kind of showing here. Okay, one more example. And this says, can you take one equation, like we ended with here on my last thing, and can we turn it into two parametric equations? Okay, I need to stress this. There are infinitely many pairs. There's no, okay, I need to be careful. There are many, 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 many right answers. There's also wrong answers. So I don't want to say there's never a wrong answer. So as long as the two go together, you can have an infinite number of right answers. So everybody in the class could have a different set of right answers, okay? The question is, how hard do you want to make this? And I really want to stress that. How hard do you want to make it, okay? So for example 5, it says, find two different sets of parametric equations for the exact same equation, y equals x squared minus 25. In my mind right now, I'm thinking, I have a parabola. That's what I'm doing, okay? So for my first one, this is what is definitely easiest. You have to make up your x equation using t. Hint, the easiest thing to do is say x equals t. That really is. So if x equals t, what does that look like for my y equation? Well, I'm going to plug in t for x. So I get y equals t squared minus 25. Done. Okay, that is my first one. That is one example. It's the easiest. Go with it if you can. Okay, but they asked me for at least two different sets. So let's do another one. So if I can't do x equals t, what about if I do x equals, let's say, t minus 1? Okay? So it's like saying 1 less second from before if that's what t actually stood for. So what I need to do is I need to take y equals, and I'm going to plug in now t minus 1, square it, minus 25. All right, let's go ahead and do some math here. That means I'm going to FOIL t minus 1. I get t squared minus 2t plus 1. Then keep that minus 25. I can simplify that to y equals t squared minus 2t minus 24. And once again, if I graph these two together, t squared minus 2t minus 24, I will get the exact same parabola, whether I do it in a rectangular form to start with, whether I do the first parametric equations or the second parametric equations, they will all end up with the same thing. And you can see that if you wanted to come up with a new example, you could make x equal t plus 5. You could make t plus 273. My guess is the numbers would get ugly, but that's really all you need to do to find out different examples. All right, have fun with parametrics. They're slightly easier than rotation of axes. You can see at the bottom of my page here, I have some problems to suggest to you. Page 932, 3 through 51 by 3s, 53 through 56 all. Once again, I'd probably stick with the odds that I can look up in the back of the book, or don't forget, you can always go to slater.com to look at what they offer for some work and answers as well. Let me know if you have any questions.